All right, so we had a brief look at the link here for playing with the ramps, and I'll throw that link on the Schoology page if you want to play with that as well. Let's talk about motion on an inclined plane. So what I'd like you to do is I'd like you to draw that picture. If you want to title your notes, it's just motion down an inclined plane. All right, so yes, I'd like you to draw that ramp, put the block up there, and then a little triangle, and Corey needs to put his phone away so he can concentrate. All right, so the angle of the ramp is theta down there. This force straight down. Now, when I say straight down, I mean straight down, like straight down to the ground, right? Is the weight force is equal to mass times gravity, right? Okay? And as we already saw earlier, and I should have had this on here as well, there is a normal force right there, right? That is perpendicular to, if I go like that, does that confuse things? Yeah. It's perpendicular to the surface, right? All right, now what these guys here are, these are the components of the weight force. Now if the ramp was flat, now do I still have it? Yeah, I do. If the ramp is flat, then, oh, let's reset. All right, if the ramp is flat, then the normal force and the weight force are straight up and down and balanced, right? But because it's not flat, then they are not balanced, which means there is a overall net force. Right? There is an overall net force, and that's what this FD is. So these are the components, okay? So what I like to do is I like to call this Fn, okay? Now, it's not technically the normal force. I should probably have a better name for it now that I think about it, okay? But I think I've sort of got it ingrained in my own vocabulary too much. But it's simply, it's numerically equivalent to this normal force here, right? These forces are numerically equivalent, just opposite. It's really, I guess, if you want, it's really the negative Fn. Okay? Now that leaves this component of the weight force down here, which I like to call Fd. Okay, and it's Fd, which is the net force, which sends it down the ramp. Now stop and think about these angles. If this angle here is, say, 20 degrees, what would this angle in here be? What, Jesse? Also 20, right? Does that make sense to you? I can show you on here, right? If I go like this, the angle of the ramp is 0. What's the angle here? 0. And as the angle of the ramp gets bigger, down here, what happens to this angle down here? It gets bigger at exactly the same rate, right? So in other words, this angle here and this angle here are equivalent. So I'm going to put a little theta in there as well. Oh, what happened there? I'm going to put a little theta in there as well. Okay? Now, quite often I like to show this FD right here. This FD right here is a component of the weight force, but as sort of a free body diagram, we like to show it up here. So this and this are the same. This is also FD. Okay? That all sound good? More or less? So, when an object sits on an inclined plane, two things happen. Gravity acts to pull it down the plane, that's that FD. And you don't need to redraw this, this is just for explanation purposes. Two things happen. Gravity acts to pull it down the plane, and gravity also acts to push it against the plane perpendicular to the plane. Okay? In other words, part of that also is the normal force, right? Now, a weird thing happens as the angle goes up. Now here's where the math comes in here, okay? So from that little triangle there that has this at FD, has this at weight force, and has this at normal force, right? Now remember, that's not technically the normal force, it's just numerically equivalent to it. It's just T used to say the force that is numerically equivalent to the normal force. So I'll just call it normal force, right? And if this angle here is theta, then I use basic grade 9 trigonometry. That's 90 degrees, right? So from this, sine of the angle is opposite, FD, right, over the hypotenuse. Now the hypotenuse is my weight force, which is equal to mass times gravity, right? In fact, I probably should have above here opposite over hypotenuse, right? So in other words, what you get is that the FD is mg sine theta, and I put a box around it because that is a formula. Will it always be sine? Like, you know how sometimes the sine and the cos, like in components, the x could be the cos, the x could be the sine, okay? It's always going to be sine because this triangle is always going to be like that, okay? This angle is always going to be theta, and the side opposite is always going to be the FD, and so FD is going to be equal to mg sine theta, and that is just simply true. It's kind of a formula derivation. It's a really simple one. Okay? Because the normal force is adjacent, cosine theta is adjacent over hypotenuse, right? Adjacent is the normal force, hypotenuse is FW or mg, so I get cos theta equals Fn mg, and here's the second formula that goes with it. Fn is equal to mg cos theta, and that's always true. The normal force is always mg cos theta. Always. Okay, so here's the sample question. I'll give you a minute to jot it down. Pretty basic. I got a 30-degree ramp. I got a block that's a meter from the top. It's 5 kilograms, and I'm asking you to find... Now, I would not normally ask you to find all those parts, but I'm just showing you the steps you would need to do to get to something like the velocity block. So we're going to find the weight force, the normal force, the FD, the A net, and time to get to the bottom of the velocity block. Okay, now, hold on here. That seems like a little bit blank page. Okay, so first step was to find the weight force, right? Which is pretty straightforward. Weight force is always going to be equal to m times g. If you don't know where to start on a problem, your best bet is to start with the weight force. Nice, good mistake. Okay? I might give you a mark for finding the weight force. So in this case here, we've got a 5 kilogram block.
Let's make a deal that you always give us a mark.
5 times 9.8. It almost always happens because you almost always need it. Okay? 49 newtons would be the weight force. Okay, now I think, I got newtons or meters per second squared. But because it's weight force, then I measure it in newtons. Right? Okay, now the next thing is the normal force. Now the normal force is always mg cos theta. So here, in fact, Justin, this might be an example where I might not give you a mark for the weight force because really, you're just going to use it here, right?
So give us a mark.
So it'd be like 5 times 9.8 times cosine is at 30 degrees. Okay, so 5 times 9.8 times cos 30, or 42.4. It is. Now that's a real good question. Is it not negative? I'm glad you brought that up, Chris. So if I put a negative in there, well, the problem with doing it like that is that negative is this direction, right? So FD, like if that's negative, then opposite must be positive. So what direction is that? It can't be positive, it can't be negative because it's somewhere in between, right? Now we could use our north, south, east, west, but that really doesn't apply because we're not looking sort of like down on a map. We're looking sideways on a ramp, so that really doesn't apply. So the direction of FD is down the ramp, right? So if I put a negative in there and I end up with a negative in there, is that 42.4 straight down or is it down the ramp? Actually, this one is up. right? So yes, it's negative, but it doesn't really apply here because what we're trying to find isn't in the same direction. Okay, does that make sense? Okay, it's a real good question though. Just doesn't apply here. The negative side. Now FD here is going to be mg sine theta, which is going to be 5 times 9.8 times the sine of 30, and that one is 24.5. Okay. Should the 42.4 and the 24.5 add up to 49? They shouldn't because they're vectors and they got angles in there, right? Okay. So no, they shouldn't add up to that. Okay. So this FD is the actual force that's taking it down the plane. Now, is there any other force acting opposite to FD? There would be, but there's no mention of friction here, and so you have to assume that it is frictionless. There's no mention of friction whatsoever in the question. You're just going to have to assume that it's frictionless. Okay? So what that means is, right, because the net force is going to be FD plus FF, but there's no friction force, right? The net force is the FD. The net force is the FD, and simply because the friction force is equal to 0. Okay? The net force is the FD because the friction force is 0. So now when I'm asked to find the acceleration, the net acceleration, I can use F net is equal to MA. And what's my F net? About 24.5. A. And that gives me an acceleration of 4.9 meters per second squared. Now, back to Chris's question with the negative, what direction is that? Like, is it positive 4.9? Is it negative 4.9? Technically, it's down the plane, right? The acceleration is this way, right? The acceleration is that way. And that's neither positive or negative, it's down the plane. If you really want to get sticky, I should write 4.9 meters per second squared down the plane, or down the ramp. I'm not going to bother with that. Okay. And now that you've got the net force, then, like, F net is remember, it's the bridging formula. It's the formula that takes you from all the forces, all the dynamics, takes you into speed and all the kinematic stuff, right? Because it has the A in it. And so now with the acceleration, I want to get the time at the bottom. So I can use d equals VIT plus 1/2 AT squared. The length of the ramp was 1 meter. Assume it's at rest. Things tend to start at rest at the top of ramps. 1/2 of 4.9 times t squared. Do I need to do the math steps here, or do you think I can just write t equals? Just write t equals. I don't want to confuse anybody. 1/2 of 4.9 would be 2.45, right? 2.45 t squared, giving me t is equal to the square root of 1 over 2.45. 0.64 seconds. Oh. The last thing that we're asked to find is the velocity at the bottom. Vf equals Vi plus At. Initial velocity is 0. Acceleration 4.9. T squared is 0.64, giving me a speed of 3.14 meters per second. Have you ever seen that the video where the guys they put up that giant slip and slide on the side of the hill, and the guy goes down and he goes flying across. You've probably seen it. Well, into the pool, yeah, that's the one, right? We will watch it because when we do projectiles, I'll show it to you, right? But then the Mythbusters did it, right? Okay, so they would do exactly something like these calculations, right? They would have to figure out what, they reduce the friction as much as they could, right? They know the length of the ramp, right? They could figure out how fast you're going and theoretically where you should land. We're going to actually be doing that in class with the Hot Wheels car, figuring out where the Hot Wheels car is going to land. It's a little safer than going on a slip and slide down a big hill. Plus, there's not a lot of big hills.
Into a lake or something?
Yeah, they thought that might be a little safer than trying to hit a little rubber pool.
Let's watch it.
Yeah, we'll get to it.
Right now?
Not right now.
Why not?
Because we're not doing projectiles. Okay, so this is an important distinction as well. On a frictionless surface, because the net force is equal to md, okay, what this means is this, and just watch and I'll give you a chance to write it down. If the net force is equal to Fd, the net force is equal to ma, the Fd is equal to mg sine theta, and guess what happens? The masses cancel, and so, as a rule, acceleration down a ramp is equal to g sine theta. Only true, though, Calvin, when it's frictionless. Okay? So that will actually speed things up quite a bit for you. What steps could I have avoided in this question if I'd known that A was equal to g sine theta? If I'd known that A was equal to g sine theta, would I have had to do this, and this, and this, and this? Instead of doing all that, I could have just gone A equals g sine theta. 9.8 sine 30. Watch. A is equal to g sine theta. 9.8 sine 30. Well, I'm running out of room here. That's 9.8 times sine 30.
4.9.
Mm-hmm. Okay, so that's a bit of a shortcut if you know that it is frictionless. You don't have to go through all this step here. Okay? All right, so there's some questions in the book there that you can do, and I do have a sheet, and I think I've left in my mailbox downstairs. There's some textbook questions. Tomorrow we'll discuss friction a little bit. You'll have a chance to do some work on Thursday for the whole period.
Who's watching?